Well, hello again. Thank you for having me in this session. So today I'm going to talk about the digital twins. And I was very impressed with the previous presentation. Last week, I asked my team to go and evaluate joining that digital twin consortium. So I can see now the big value that uh, membership could bring. And um, what I like to do today is show you additional perspective or information about what is a digital twin, and also try to show some examples, particularly the ones we have built in the lab. Our application focuses more on the human digital twin. And because this group is smart cities, I just have some ideas and information to show to you on this aspect. And then because we're here in Star Park and Andres and I are co-directors of CEDAR, we can talk about potential collaboration opportunities, particularly on the Living Lab at Star Park. So again, my name is Jesus Jimenez. I'm a director and a professor of industrial engineering at Texas State University. I joined Texas State University in 2006. Back then, we were just a department, and I've been having the pleasure to participate in the growth of engineering at Texas State. And I have done my first work as undergraduate was a project in simulation. And ever since I've been connected to this area. What we did back then, a group of us were developing a simulation model, discrete event simulation, and a tool called ProModel. And basically, we model a twin factory that manufactures medical gowns, and they asked us to develop this animation of the model of the real process, and we put that model into the software. Requires a lot of effort in terms of building the solution. There's nothing like generative AI. There was nothing like that back then, so there's a lot of effort required to build this model that includes the data collection, the actual programming, and then later the analysis, so that at the end, we provided recommendations on how to improve the manufacturing system. So these projects typically are months just to develop a project like that. So later, we developed something called the visual interactive simulation, because we wanted to have some sort of way to tell the simulation how it should react to the changes in manufacturing that are very dynamic. So we wanted to have a perception of how those changes will impact things like the cycle time, the throughput, and WIP. These are very common activities done in the manufacturing performance evaluation. So that's another part that helped me to motivate on this concept. And then later, during my PhD studies, we developed models that for semiconductor manufacturing, specifically the wafer fab and the material handling system. And those fabs, I know we'll share the panel with Joel later. And these simulation models are very complex. They require hundreds of processes and lots of different components. Plus, you add the material handling activity, it becomes a very time-consuming event. So to produce the simulation model, they require a lot of time to run, to maintain, and typically these big companies have teams, large teams dedicated to sustain the simulation effort. And all of these models have been used to make decisions about where to build the next fab. These fabs are billions of dollars, so the decisions are very important. So when to build it, when to add capacity, when to add new machines, when to change the technology. They are very useful to answer those kinds of questions. And as I said, the experience has been that building all these solutions requires lots of knowledge, but also lots of effort. And for manufacturing companies, they are often require solutions to be very fast, using tools that provide very fast solutions. So that's how the motivation for the digital twin, at least my passion to be involved, started. And this brings me to my point that I want to make. It's what is a digital twin? So I explained simulation effort, and often that is a concept that is confused with a digital twin. The digital twin is basically a representation, a virtual representation of a physical object. So the potential is huge because for every physical element, you have now an extension that is also in the digital world. So the idea with the digital twin is that it is connected to the physical counterpart. The connection is to be in real time. We saw just an example of that car, and therefore that connection of the actual racing car is connected to the digital twin in real time. It means that it's collecting a lot of data as it is running. So it requires the use of sensors to be collecting huge amounts of data. And then it needs to do some processing. And that processing needs to also be real time so that it can give recommendations about changes that you want to make to the system. And therefore, those recommendations also need to be done in real time. So that requires artificial intelligence tools or other tools that give you those recommendations. So that is that definition in my mind about digital twin that is very important. There's a lot of connectivity, data collection, and output, and those are done in the real time. This is one of my favorite charts, levels of integration, and this is just describing what I mentioned, that the perception of the digital twin is that it's just a simulation or just an AutoCAD, but what it shows is that you have the digital model that is a representation of the physical system, but a lot of the data that you're collecting, a lot of the analysis you're doing is very manual, and as a result, doesn't have that reaction time that you expect from the digital twin. And then you have an evolution in the level of integration and the level of connectivity with the physical object that takes you all the way to the digital twin so that everything is automated. And that is the other component of the digital twin, that you can have such static integrations, but also you can have the real-time dynamic integrations. Another good benefit of the digital twin is that you can have very nice visualizations of the performance metric of the system. And those visualizations help to communicate the user aspects that you can learn from the system. You can also communicate data that is very well presented so that you make some decisions on your system. And then what are the digital twin levels? So the digital twin can have actually multiple digital twins as components. So you have the higher level digital twin, but you may also want to build your system so that it has other digital twins inside. So therefore, with that level of hierarchy, you can have digital twins that are at the part level. And having digital twins of the part allows you to monitor things like the health of the part, the reliability. You can have preventive maintenance types of applications. And then multiple parts make the product. So you can have a digital twin at the product level that then you can use to assess the life cycle of the part, and then you can use it for product development or testing. At the part level, then the next level will be process. And then when you have the digital twin of your process, you have opportunities to plan and control your production. You can schedule your orders, and you can have also process optimization. And at the end, you have the highest level, which could be a supply chain, a factory. It could be a smart city, basically a digital twin of the entire system. And here, that's where you have collaborations, because it might be necessary that one supplier access the digital twin of another supplier or another entity, and therefore you need to establish some way to exchange data communications between the different digital twins. I heard recently of a talk from the AI Institute that they were sharing the idea that digital twins can be assets that people can own, and therefore I, as a user, can develop my digital twin, have some property of that digital twin, and then you can rent it or make money with sharing your digital twin. So that's very impressive to me. Great opportunity for growing this type of infrastructure. Now, let me show you some of the examples I was referring to. I want to point out that digital twins, they have, and as in the previous talk mentioned, they have different industry applications. The ones that I have seen very mature is in the aerospace industry, manufacturing industry, but you also have applications in healthcare, public services, energy, agriculture. In this particular example, it's a digital twin built by Siemens. Let me just control the volume here. Okay, and these are examples of what the digital twin capabilities can provide. You have, in this case, a manufacturing cell, and then you have your process. You have all the workers, robots, and this type of application allows you to study all the interactions between the objects and humans, the exchange of information, so that you can predict for these particular systems. It's very important to know what is the time to produce one of their batteries, and how much inventory they will have. They can test multiple scenarios, like the layouts of the process. You can also determine things like what happens if the manufacturing operator needs to take a break. What's going to happen to the environment if you need to reschedule the tool. And then it gives you opportunities to interact and design the space, the workspace. In some cases, you can look into the ergonomics aspects. And that gives you a lot of capabilities in terms of understanding what kind of efficiencies you can improve in your system, so that the bottom line of the company improves. You can integrate that with the facility, and then look at other aspects like the infrastructure and how that infrastructure interfaces with the production system. So that's one of the examples. Most of these digital twins, to get to that level, these companies, they start building small cases. They start with a machine, and then they start building the teams and the expertise required to build that digital twin. You expand it to the machine level, to the line level, and then you can get it all the way to the factory level. So it grows and matures by the by the type of system that you have. This is another example where this concept of the real-time interaction plays into effect. Here you have the robot. On the right side, you have the physical object, and then on the left side, you have the virtual object. And as you can see from that video, the reaction time between the physical object and the digital object, they're almost instantaneous. This is more about the research that we do in my lab at Texas State. We're motivated by material handling operators, particularly in warehouses. This project was funded by Toyota Material Handling Industry. Those companies are the ones that produce the forklifts that you see in the warehouses with the Toyota brand, of course. Then what we were looking at is to develop the digital twin for the human operator. And we did this in the lab. Initially, we had cameras, optical cameras, that had or collected the motion of operators as they were moving in the operation. So in the background, you see that optical camera. One of the aspects of this is that this digital twin in particular collects also physiological responses from the operator. So you can see heart rate, respiration rate of the operator. We're also interested in the cognitive functions. So all those data are collected. Now, our digital twin is specifically, we are trying to accomplish the real-time connectivity and the real-time response, meaning that we had to do the development of the machine learning so that we could understand in this particular machine learning tool, we were interested in predicting the fatigue of the operator, seeing when the operator will be tired, and then when the operator reaches that exertion point, we will do some intervention. So we have different aspects of this tool. Like in this particular case, we have the real-time, the physical experiment, and the operator there is doing the physical simulation of the activity. Let me just make a quick point right here. So on the left, you have the actual digital twin. Again, the interaction is real time. And in our case, we were using the machine learning tool to make predictions about the fatigue rate of the operator. In our case, when we built these fatigue models, we found that they're highly correlated to heart rate. So that was a key metric for us. And we use HoloLens. In this particular case, you see the Unity environment. So now with the HoloLens, you can project and you can see the operator doing the activity, and then you can see multiple angles of that operator. So these are kind of key tools in manufacturing, because one of the aspects is when the operators, they are going to retire, but you have a star doing the exercise, you have the capability to record the digital twin and save that virtual copy so that you can later train other operators. So that's one of the activities. Also, this particular instance, it was detecting bad motions, bad postures. So as soon as you had a bad posture, there would be some cue, some signal, feedback real time that basically tells the operator that he was doing a motion that was not properly done. Now, as I show you, we had these cameras in the background. These are very expensive. So one of the feedbacks that we got from the companies, well, these are great, but then this is just lab-based. what can you do to take them to the real environment? So our next project, which is what you're seeing here, what we did is we took the video, but now using conventional webcams, and there are open source software that can monitor the coordinates of the operator. In this particular instance, we're also integrating. We used to have those body suites that are used by NASA, but in this particular case, we're using something very conventional, which is just like an Apple Watch, just to collect information about the physiological aspects of the operator. And then we put this in a software platform, pretty much what you will see if you use these exercise machines like Peloton and those kinds of things, using that kind of graphical interface so that the operator can see their performance as they do the exercise. So that is our current interest right now, building the tool and building additional artificial intelligence tools so that we can recognize motion and detect fatigue levels. Our recent module integrates ergonomic assessment, so it does an ergonomic assessment on the exercise and the posture that the operator is doing in the exercise. By the way, Harold, this is an activity we have in your lab, in one of your labs. It's we're working right here on this project. And then the capabilities of this tool is basically you can I'm trying to advance this. Well, we have later a video. It's just gonna get there, but then you can apply the digital twin to other highly commercial applications, and you can see that the tool reacts very well to the operation. In that case, the operation was pre-recorded, so but the application of the tool, there it is. You have an operation. This operator is working at a very high speed, so the digital twin is responding so that you can do some real-time time study. Time studies in manufacturing facilities are typically done with video cameras, and you have people just dialing work. So in our application, we're doing the digital twin to do the time study, and it's recording the cycle times between the different processes. And that is very useful because these real times, these time studies, as I said, they're very time consuming, but this tool can do this almost without effort. Okay, next. So this is a digital twin of a smart city. This is just an example available in the literature, but it shows very similar components to what we have seen in manufacturing, where you have your artificial intelligence, big data components. You have IoT, cloud, and 5G technologies so that you can collect the data. You analyze it with your artificial intelligence and big data analytics. You can provide visualizations. You can make predictions. And all of the different layers that you can build, you can have the land, the building, the infrastructure, mobility, the digital layer, and then the virtual layer, basically communications between these two. And I think the smart cities, there's a lot of penetration already, because if you go, there's a lot of opportunities right now. Like you have the Google Maps, you have Apple Maps already. They give you information about traffic, and users are very used to those kinds of tools because now you have those apps that help real life day applications and help people make decisions about their planning routes. You have information about the weather. You have information about temperature sensors. There's a lot of technologies being developed, and the opportunities are huge in that aspect. And then another common application is to have the digital twin of your facility, and then try to monitor space, monitor flow between the rooms. You can look at temperatures, you can look at humidity levels, and therefore that type of information is very useful, particularly when you're planning to do these designs and improve efficiencies of these designs. So that particular space is growing increasingly. That's what I wanted to do, just give you definitions of the digital twin and some applications that we have seen, and some of the opportunities is that this market is pretty huge. There's 25 to $50 billion in the market, and there's still a lot of opportunities, particularly technology gaps, sensors, platforms, data sets, training the AIs, so that you can actually enable a true real-time digital twin. And then the operation of the digital twin still needs to be further developed. There's a lot of testing opportunities. And this is where, the call for action is. In Texas State, we have developed these programs I mentioned in the morning about the proposals for the PhD programs. These have in their design the digital twin in mind, in the different areas: electrical, civil, and mechanical manufacturing. Those are the different PhD programs that we have proposed. But we have those as part of the curriculum. We're going to teach our students, when the program receive approval, these different components, and we have a digital twin course included as part of the curriculum. At the undergraduate level, we're exposing our students, particularly in the civil engineering and the mechanical engineering, to these technologies. We have the technology enhanced infrastructure and the Industry 4.0 as part of the core concepts of our undergraduate programs. So the idea, for instance, in the technology enhanced infrastructure, we have faculty doing research that are including sensors in the infrastructure, so that you are collecting information, particularly about the health of the infrastructure. And they're also learning how to analyze that data, so that that improves the life cycle of the design. There's faculty that are interested in the digital twin component and the different technologies associated with it. And there's a lot of good people that are already working on digital twin types of applications, including the one that I just showed you in my lab. And as far as collaboration opportunities, this Star Park, and one of the visions that Andres has is the living lab concept. And if you have talked to him, he will tell you Star Park is a living park. And basically what that means is that each of these buildings, roads, street lights, those are components or parts that are elements of the ecosystem. If we put sensors there, if we put those kinds of technologies, we will be able to capture data, develop the digital twin of the Star Park, so that we can test many different things. We can test technologies, different technologies that you have. We can test algorithms, we can test data, we can test all the, we can do the troubleshooting, which is very important for us to grow this concept. So if you haven't talked to Andreas, please, I encourage you to do that. These are great opportunities that we have here. And from the academic side, we're training the students, the workforce required, so that they can interact with your company. So, anyways, that was my call for action, and I want to thank you for your time. I think we have time for questions, right?
Yes.
You happen to have an energy industry example, and you listed energy. Is there an example behind that?
The example I provided was only on the battery manufacturing cell, but I'm sure we can get you some applications and send you some information on that. I don't have an example right now.
What I can add to you all is that as we're building the 14 living labs, we are planning to use all the disciplines of engineering to do research, concrete, construction, mechanical, electrical, industrial, and all of the above. And as we're building things, we're starting to realize that we need to use all the technologies, drone, tracking things, recording things, connecting things. The buildings will be low carbon footprint, zero energy, water retention, water capture. So we are going to eat our dog food, and if that's the key about what Jimenez wants to do, he keeps giving me credit, but I give him credit.
No, thank you. Please.
Can you allude to some of the case studies in digital twins in healthcare and public services? Really interested in those sectors. I've got 3 questions, by the way. And the second one is, what kind of use cases do you see for the human digital twin that we created? In thinking about like organization, when you talked about ergonomics, is it like from the organization side of things, like for the whole employees, or in healthcare where you have repetitive tasks? So we'd love to hear what your vision is with regards to the human digital twin. And the third one is, you showed the city of, you said office in Toronto. Is that your office in Toronto? I live in Toronto, so I'm just really curious. Is it the city of Toronto, so?
No, this is one of the use case studies we found on a particular software company that developed that particular digital. Yeah. No, we don't have an office type of digital twin, but I just wanted to show that this application can exist. Yeah. Regarding human digital twin, when we were starting to think about this concept of digital twin, actually, back then my colleague and I have another colleague, Dr. Mendez, and we were thinking about application of future space. And one of the things that we probably were not visionary, but just dreaming about potential human exploration in other planets, and what would it take for somebody in Earth to monitor an astronaut or an explorer in that space, including all their health and all their physical activities. So that was our motivation in terms of applications of human digital twins. There are a lot of research being done in terms of developing this. There's people thinking about, looking at different the health of the organs and how they are, affecting your health. So that's the kind of research I have seen. There's a lot of interest right now in the cognitive functions, and seeing the cognitive functions, how they affect the performance of a human. In our case, we're including the cognitive function because fatigue is hard to predict. It's not only a metric that you can predict through your physiological responses, but there's also things you can use with motion, but cognitive functions. We actually have done this experiment of lifting and lowering, and ourselves, we get tired, and there's nothing in our physiological responses that would explain why we got fatigue. So there's this element of, my mental activities declining, and how that influences my productivity. So these are the aspects that we are considering in terms of.
I was thinking more broadly of the day-to-day practical, like when you take healthcare, there's so much repetitive tasks when it comes to diagnostics and lab. And I used to lead healthcare, and we used to have at least 28% to 33% of chronic long-term disability because of that functionality and then the issues that they have. So I was just really hoping that it's the day-to-day application, but it's cool though.
Yeah, we have in one of our user cases we are developing right now. We have a project with the Texas Workforce Commission, and one of their programs is to manufacture products with using workforce that has disabilities. These are people who may be blind, and they are trying to produce a product. So in our case, we're trying to find how to improve the operation and look at in their cases they use the hands a lot. So what kind of factors it would affect their health? They have to rely on other sensor, like another information, not the side, but they have to use other touch or sensory activities so that they perform the operation. And sometimes they get tired, and they show that by touching things or resting their hands. So that's the kind of application we're looking recently, how the digital twin can predict when that person is fatigued and needs to rest. So definitely the health space sector is a huge application, is growing. We're seeing research papers that are being proposed to explore digital twins. It's a complex subject. For us, we are just using low tech so that we get the information. When you're going to the digital twin, it requires data that may be invasive to collect. You may require some instruments to collect, and therefore that is a challenge for us in our case. Thank you. Well, thank you very much.